Assalamu alaikum. This is lecture 7 of machine learning, and in this lecture I am going to elaborate more about discriminative models. In earlier lectures we discussed briefly about different kinds of models such as probabilistic, generative model and discriminative models. Apparently in this lecture we are going to further classify and differentiate between these two kinds of models. And mainly the focus of this lecture is on the linear discriminant models, and we will employ several techniques to test and formulate discriminative models. And one of the famous algorithms for discriminative models is logistic regression. Although we have discussed about the two algorithms, the perceptron and the logistic regression, in one of the previous few lectures, however, in this lecture we will mainly focus on these two algorithms in terms of their discriminative feature. So finally, I will provide an comparison between a generative Naive-Bayes method and a discriminative logistic regression model. So at this time, you must be familiar that we have been discussing the Naive-Bayes algorithm since the inception of this class, and you should know the particular formula to calculate the Naive-Bayes, and you are well informed about the Naive-Bayes calculation. And in the Naive-Bayes we have to calculate the likelihood of an outcome along with the probability of that particular clause, often termed as prior probability. That is the conditional probability of any feature with respect to given clause, positive or negative in terms of binary classification, or any other label in terms of multi-label classification, and the prior probability of that particular class. So once again I will elaborate it with an help of an example. So let's take an example to predict a disease or a particular patient's test. So let's say we have three input features and we name these input features as fever, number two cough, and number three fatigueness. And let's take one output label as a binary classification for the outcome of the disease or the test as positive or negative. So now we have three input features and two output classes. So the naive-Bayes assumption says that you have to calculate the conditional probability for each feature for particular class and multiply it with the conditional probability of that class. So let's say we have a new patient and we diagnose that he has fever and he is also feeling fatigue, but he is not feeling any cough. So our first assumption is to calculate the likelihood of each parameter or each attribute with respect to the positive clause and with respect to the negative clause along with the prior probabilities of each class. So now calculate all of the probabilities when your test data have fever is equal to true and the clause is positive, and then for the second time when the clause is negative. Secondly, calculate the probabilities when fatigueness is true in your dataset for positive and negative class. Similarly, when there is no cough and you calculate it for positive and negative class. Then multiply it with the probability of positive and negative class for each value. Sum up the values, and if values for positive class is greater than negative class, your outcome will be marked as positive. So at present moment, I believe we have discussed about both of the methods in considerate detail. The generative models generate the data samples from the data sets and produce the actual probabilities for each class. So in summary, generative methods such as Naïve assume some functional form in terms of probabilities of inputs and outputs, or in simpler terms, the conditional probabilities for each attribute with respect to the target values and prior probabilities for each target class. So they estimate the parameters in terms of likelihood and prior probabilities directly from the data. For example, you model the class conditional probabilities together with the prior probabilities for the classes and then compute the required posterior probabilities using the Bayes theorem. So in the simpler term, you should have another method to learn these probabilities without the prior estimates. So why not learn the posterior probabilities directly? Or better yet, why not learn the decision boundary directly, which differentiates different kinds of classes or labels? So for that we have discriminative classifiers. So for this case we use a common discriminative classifier, which is logistic regression. So discriminative classifiers assume some functional form in terms of posterior probabilities or for the decision boundary. So these methods estimate parameters directly from the training data, and they directly assign each vector input attribute to a specific class, such as positive and negative in the binary cases, or any class C of k in a multi-label classification. So linear discriminant functions have similar properties, much like the linear models discussed in the lecture 4. So linear discriminant function for a vector x should be equal to a linear method which we used to denote as a y of x is equal to w transpose x plus w0, where W is called the weight vector and W0 was a bias term. The classification function was usually the sign of this output. So if the sign was positive, we say that our example is greater than 0, and if sign was negative, we can say our example result was less than 0. So in other words, it classifies a positive and a negative example discriminatively. So here are some properties of linear discriminant, and the main feature in the linear discriminant is that it has a decision boundary. So the decision surface here is shown in the red line, which is perpendicular to the our weight matrix, and its displacement from the origin is measured and controlled by our bias parameter weight 0. The signed orthogonal distance from the general point x from the decision surface is given by y of x over w. So it is the distance from the decision boundary to the actual location. So y of x gives us a signed measure of perpendicular distance r of the point x from the distance surface. So if y of x is greater than 0, that means our point lies into the positive deviation or into the positive side of the classifier, and if our y of x is less than 0, we classify the example as negative. If our y is equal to 0 or y of x is equal to 0 for x, therefore that point will reside onto the decision surface. The normal distance from the origin to the decision surface is provided by the formula here. So again, W0 determines the location of decision surface. So the decision from the surface is calculated from the orthogonal projection. So let we have a point x, its distance from the decision boundary is calculated by an projection x, orthogonal projection onto the decision surface by this formula. So where this variable is the projection of x to the decision surface, then we multiply both sides with the weight transpose and add the term W0 onto the both sides, and making use of y of x is equal to Wt x as our method. Similarly, we have an assumption which says projection of y is always, projection of x is equal to Wx plus W0 is always equal to 0. So by substituting these values, we get our distance from the decision surface by the following formula, which is the our linear method divided by our feature weight attribute. So we introduce additional dummy input value which we have been introducing in the previous few lectures. With the W0 we include x0 is equal to 1 and then define W bar is equal to W0 and our weight matrix, and x bar is equal to x0 which was equal to 1 along with our attribute, so that our y of x becomes W bar t into x bar, which is again a linear discriminant function. So that means it can divide the positive examples from the negative examples. So now consider the extension of linear discriminant where you have more than two classes. So we might be tempted to build a multi-class discriminant by combining number of two class discriminant functions. That means if we have three classes, we can use three different discriminant functions, and each function is a binary discriminant function which classifies each class from the rest of the classes. So if we have three classes C1, C2, C3, our binary functions in the first case, first binary function will treat this class as positive and both these classes as negative. Second may treat this as positive and the rest of the data as negative. Third may treat the third as positive and the rest of the data as negative. However, this leads to some serious difficulties. So this is often also termed as one versus the rest classifier, which is used to classify the class labels and samples not in that class labels. So this image shows an example of having three classes where this approach leads to the region of input space that are ambiguously misclassified or ambiguously classified. So according to this feature, as you say, you have employed two binary functions, and the first linear function is this and the second linear function is this. So once you have the linear boundary, you can say all of the items classified here belong to our class label 1, and on the other side of the boundary these belong to not class C1. That means they can be anything but not C1. Similarly, you have the second classifier which classifies using this linear method, and the examples correctly classified are marked C2 and the rest of the examples are not C2. So you have the definition of different regions, region 1, region 2 and region 3 respectively. However, there is a fourth region where the ambiguity lies, because this also classifies as C1 for the first linear classifier and C2 for the second linear classifier. An alternate is to use a 1 versus the 1 classifier. That means classify every pair of the classes. That means use a different classifier for each class. So each point is then classified according to the majority vote amongst the discriminant functions. However, this too runs into the problem of ambiguous region as illustrated in this figure. So in this figure we have three different linear methods which only classify labels belonging to that particular class. So that means there is no positive or negative classification. In simple words, only the labels will be classified that belong to that class. So let's say we have our first classifier here which classifies the C1 examples. We have second classifier here which classifies C2 examples into the region 2 area, and we have third classifier here which specifies C3 examples in region 3. So again we may have confusion of C1 here. C2 can also be here and C3 may also, sorry, the C3 is on the right hand side. So we may have the confusion between C1 and C2 here again. However, we can avoid these difficulties by considering a single K-class discriminant comprising K linear functions of the form yk of x into wkt of x plus wk0, and then assigning a point x to class C if probability of that class is greater than probability of the other classes where those all other classes are not equal to the current class. That means we will classify our image to a cat if the probability of cat is greater than probability of all other animals, where cat is not equal to all other animals. So the decision boundary between two classes such as cat and a dog is given by two linear methods yk of x and yj of x, and you calculate this method with the weight difference of each class multiplied by the input feature vector plus the differences of biases in each class. So this eventually has the same form as the decision boundary for the two class case. Additionally, there is a way to view the linear classification model in terms of dimensionality reduction. So in this method, you pursue the optimal linear projection on which the two classes can be maximally separated using the linear function y is equal to wtx. So if we place a threshold on to the decision boundary so that if the and classify the CN greater than equal to our negative bias as class C1, and if that is not the case, the otherwise class C2 will be assigned. So then we obtain our standard linear classifier. So that is the same classifier which we have been discussing previously. So by adjusting the components of weights vector W, we can select a projection that maximizes the class separation. So to begin with, consider the two-class problem in which there are n1 attributes points of class C1 and n2 points of class C2, so that the mean vectors of two classes are given by the M1 and M2. So once we differentiate between different classes examples and then project those onto the linear classifications, and after the projection the two classes are separated as much as possible. So these are measured by the distance between projected centers using the following formula. So by extending the formula, we get the term WTSDW. So where SD is equal to M1 minus M2 into M1 minus M2 transpose, and which is called between class covariance matrix. Once the two classes are projected as wide as possible and the variance of two classes is also measured, which should be as small as possible. So as much like the variance of between classes was represented by S of B, the variance of within classes represented by S of W, and the our interclass within class variance is measured by taking difference of each example from the mean of the first classes and for the difference for each variable attribute from the mean of the second class. So consequently, the projection is shown into the following figure. So the left plot shows the samples from two classes depicted in red and blue. So as you look at the histograms provided here, resulting from the projection onto the line joining the class means. So you can see that there is a considerable overlap between two classes or projected spaces. The right plot, on the other hand, shows corresponding projections based on the Fisher linear discrimination, showing a greatly improved class separation. So this philosophy works on the Fisher's criterion, which is defined to be the ratio of the between-class variance to the within-class variance, and it is given by a cost function. So again, SB is the between-class covariance matrix and SW is within-class covariance matrix. So differentiating the cost function with respect to weight matrix, we find that cost function is maximized when we find Decision directions. So furthermore, we do not care about the magnitude of the scalar values, only about their directions. So we can drop the scalar factors such as Wt SBW and Wt SWW along with the transpose of mean difference. So applying within class variance inverse on both sides, we get the resultant weight which is directly proportional to inverse of within class variance within the difference of two means. So this result is known as Fisher's linear discriminant model, although strictly it is not a discriminant but rather a specific choice of direction for the projection of data to the one dimension. However, the projected data can be subsequently be used to construct a discriminant model. So again, it is not a discriminant, it helps you to find out the projection of data. Therefore, a bias or threshold is needed to form a linear classifier, and multiple thresholds lead to non-linear classifiers. Therefore, the final classifier has the similar form y of x sin wtx plus w0. So where the nonlinear activation function sin dot is a step function which is equal to 1 when our probability is greater than 0 and minus 1 when it is less than 0. So in this case it will have class 1 to class 2 probabilities. So another example of a linear discriminant model which we discussed in one of previous lectures is Perceptron learning algorithm. So Perceptron is inspired by biological concepts of human psychology and human nervous system. So it works on the phenomena that whenever a signal is positive, it is reinforced by another signals from the neurons. Or in simpler terms, good behavior should be rewarded, bad behavior should be punished or not rewarded in any perceptron model. So this improves overall system fitness. That means where the signal is positive, the neurons reinforce the signal, and where signal is not positive or not progressive towards an outcome, it is mitigated. Similarly, correlated events should be combined. So these are some specific terms about the neurons, and you can work on these to understand the concepts about the neuron. However, these are not very much relevant to our current implementation. Therefore, we will come back to these concepts in a later lecture. However, you can go through for your understanding. So perceptron again corresponds to a two-class model in which the input feature vector is x again, and it is first transformed using a fixed nonlinear transformation to give ourselves a feature vector, and then this is used to construct a generalized linear model in terms of f of x, w, t, and phi of x, or in simple terms, it's summation of weights into input attributes. So perceptron, as described earlier, is a weighted linear combination of input feature vectors, and it may contain some non-linear decision functions. It contains a linear offset bias. So as a simple perceptron can classify different examples using linear separating hyperplanes, such as taking the example of spam or ham emails, or novel or typical examples, or click or no click examples using linear classifiers as depicted here. So if you recall the perceptron learning algorithm, the learning was based on the estimating the parameters weight attributes and the bias term. So here is the illustration of the perceptron. You start with the initialization of weights and the bias term to 0, and you repeat until you find a linear classifier that is able to distinguish from the positive examples to the negative examples. And at each step you predict the values from your dataset and you compare it with the actual predictions. And if the resultant values of your, or the calculated values of your perceptron are less than 0 or any other threshold, you update the weights based on the prediction, and you update the bias based upon the actual prediction value, and you end the loop when all of the examples are correctly classified. So nothing happens if all the examples are classified correctly. So weight vector is a linear combination of weights, and classifier is a linear combination of inner product f of x for all input attributes y of x of I into x plus b. So in the perceptron cases, if there exists an exact solution, in other words, if the training data set is linearly separable and you have found the weight and the bias attributes that you have the unit length and correctly classify your examples with an acceptable level of performance, then the perceptron converges to a linear separator after a number of steps bounded by the given formula. So it is the bias square plus 1 plus a threshold square plus 1 into performance power minus 2. So from this calculation, we can say that the number of steps required to achieve convergence could still be substantial. And in practice, until convergence is achieved, we will not be able to distinguish between non-separable problems and one that is simply slow to converge. The perceptron is usually dimensionality independent, and the amount of features usually does not hinder the performance of the perceptron. It scales with the difficulty of the problem, and you only need to store the errors which are the incorrect classification by perceptron. So this gives the compression bound for the perceptron. So you can use a gradient descent on a hinge loss to optimize the perceptron algorithm. However, it fails with the noisy data, and furthermore, for the datasets that are not linearly separable, the perceptron learning will never converge. So this slide shows an illustration of the convergence of the perceptron learning algorithm showing the data points from two classes shown in red and blue. So these are depicted in a two-dimensional feature spaces. So this top left image shows the initial parameter W, and for each transition you have updated the weight attributes and the bias terms so that our decision boundary fluctuates. So as the first few iterations, our decision boundary lies about here. So after the modification, your boundary moves here, and in further illustration, it takes the shape of this, and finally it converges to this form. So in each illustration, feature vector is added to the weight vector, giving the decision boundary shown for all the data points that are correctly classified at any epoch. So here are some further points about the linearly separable data points and inseparable data points. And additionally, there are some realizable concepts that you are able to learn from the system or the model by distinguishing different data values. Therefore, some function exists that can be separate that can be used to separate data, and it is included into the concept space. And for perceptron, data is linearly separable. And in other words, perceptron is able to classify the data that is linearly separable. However, some concepts are unrealizable. That means where data is not separable. That means there are some situations where data of positive classes and negative classes is mixed. There may be several reasons such as noise is one of the common to create this mixture, and we do not have suitable function classes or often hard to distinguish between the feature attributes and the target classes. One of the typical examples which we have been discussing in many previous lectures is a, non-linearly separable dataset, which is an XOR. So in some cases, non-linear separation is trivial. However, in other cases, it may be inevitable. For example, as you can see in the illustration here, an XOR data is provided and you are unable to classify this data using any linear classifier. So whatever way you draw the boundary, you are unable to distinguish the green labels from the red labels. Additionally, in some cases, you may have a data which is non-linear, such as here you can see an example is drawn where data presented is non-linear. So a possible solution is to map the data into a higher feature space, such as using any feature attribute. It can be a polynomial feature. That means transferring the data into another form and then solving the problem in that space. So as you can see in the first form of the data, that was before the pre-processing, our data was not linearly separable. However, when we transform the data into a higher dimensional, such as using the three dimensions z1, z2 and z3, we can see that our data is linearly separable. So the circles are separated from the crosses. So as you can see, we can separate the data using this boundary. However, in the non-linear features, surfaces are usually circles, hyperbola, or parabola shapes. Similar is the case for the XR, which is not linearly separable. However, if you map the data into three-dimensional using the transformation methods for the XOR data makes it easily solvable as described here. At this point, I think we have discussed considerably about the distinction between the discriminative and generative approaches to the classification. However, to further clarify the concept, we use another discriminative model, which is the logistic regression. Logistic regression is an algorithm that is admirably suited for discovering the links between features and some particular outcome. So logistic regression is a sigmoid function defined by the term sigmoid 1 over 1 plus exponent of minus z. It is often said logit z. So which is plotted in this figure. The term sigmoid means the S-shaped. This type of function is sometimes also called sequential function because it maps the whole real axis into a finite interval. For the logistic regression, features can be discrete or continuous, so it works on the both kind of. So logistic regression is again a linear classifier and it takes the functional form of p of y given x, which is the posterior probability in terms of generative classifier and the prediction or the assumption of decision boundary in terms of discriminative classifier. So which is termed as for the positive classes given p of y is equal to 1 for input attribute is equal to 1 over 1 plus exponent of our linear model. So our linear model in this case is a decision boundary specified as bias term plus our weight attribute matrix and input feature matrix is equal to 0 onto the decision surface. So it may have the inequality on the positive and the negative cases, and the result of our function can be greater than or less than equal to 0. Therefore, we have a linear decision boundary. So the logistic sigmoid function plays an important role in many classification algorithms. So it holds the symmetry property for positive and negative class, and the ratio is represented as following formula. Property for the other class is represented as function of negative class is equal to 1 minus sigmoid of positive class. So once you take the minus 1 minus this expression, the result of the other class is equal to this, and taking the ratio results in the same linear formula. In the terms of exponent, it should be greater than equal to or less than equal to 1 for positive and negative example, and subsequently results into our linear discriminant function. Similarly, for the case of classes greater than 2, we have logistic representation in more general case where representation of each clause is represented as y1 to 1 yk, and for the decision boundaries of each class we calculate the logistic regression for the input attributes, and for the final class we use the term without the weights for the final class. This final normalized exponential is also known as softmax function. So it represents a smooth version of max function. So for the training of logistic regression, we have to focus first on the binary classification and our decision boundaries for positives and negative decision points is provided by the formulas discussed in the previous slides. So the task is again to learn the parameters from the weights 0 to weights number of uh, dimensions. And again we have the training data marked as input feature and the target feature as x of j and y of j respectively. So first and foremost thing for the logistic regression is to calculate the maximum likelihood estimates depending upon the input features and given weights. But again here we have the problem. We do not have the discriminative model for calculating prior probabilities or conditional probabilities of input feature vectors given the target. Instead, we only calculate the decision boundaries. Therefore, we modify our maximum likelihood estimate and calculate a maximum conditional likelihood estimate. So which is again learning of the decision boundary given input examples and weights. So in the expression of conditional log likelihood, the output can only take values 0 or 1. So only one of the two terms in the expression will be non-zero for any given output. So one estimating the conditional log likelihood, you can calculate the loss function, and you would like to minimize this loss function to achieve the accuracy in your model. So basically a log likelihood should be maximized, but in order to turn this loss function, that's something we need to minimize. So generally a log likelihood is specified as y some function into 1 minus y into some function. So taking these examples as a function, we have y into log of p where y is equal to 1 given our input, and 1 minus y into log p is equal to p into y equal to 0. So putting the values we get the same ratio plus our log of PFL into our input features. So simplifying the values we get the maximum so minimized loss function in this term. So maximizing the conditional log likelihood will result our method into this form. However, this is equivalent to the solution which we provided in the logistic regression in lecture 4. But we have a bad news here that we do not have any closed form solution to maximize our log function, or neither we can use the direct solution. However, we have a good news that our loss function is a concave function of weights, and the concave functions are easy to optimize. So our goal is again to use the gradient descent to find the optimal mates, minimizing the loss function we have defined. So we can use the gradient descent to minimize our loss function or a cost function. So we can use our formula to update the weight using the learning rate, and learning rate should be greater than or equal to 0, but it should be a controlled weight. So at each step our weights will be updated with respect to the partial derivative of our loss function with respect to our weights multiplied by the learning rate. So gradient descent or gradient ascent work in a similar mechanism for logistic regression, and they iterate until the change is less than our minimum error. So at each step you update the weights for the next examples based on the prediction on the current example or the weights that things label y should be. So as described earlier, the weights are again controlled by the learning rate. So if you set a very large learning rate, your algorithm may converge faster to the solution, but it may have a larger residual error and also possible oscillation that your algorithm may encounter during the optimization. On the other hand, if you have a smaller value of your learning rate, your algorithm is better optimized to converge, but it will take larger time in conversion, but similarly you will have a lower residual error and your algorithm optimization will not bounce a lot. Towards the conclusion of this lecture, I would again like to compare the generative and discriminative approaches. And in this case, we have the comparison of naive Bayes with the logistic regression. So as we have seen, naive Bayes is quite affirmant to perform on set of questions. However, logistic regression works on logistic or logit functions. It has naive parameters and it has the regression parameters. It is a generative model. This is a discriminative model. So as you have seen from the previous examples and the lectures, the implementation and the representation of the both models is quite same. However, we may have seen an assumption about the naive Bayes that it works with the class independent variance. But what is the main difference between these two approaches? So one of the main differences is that logistic regression makes no assumption about px given y in learning. That means no assumption about the likelihood of the parameters on the output target. And secondly, they use different loss function to optimize different solutions. So this slide further highlights the differences and their working philosophies between generative and discriminative methods. So these are taken from a paper published in 2001. So given on infinite data, and we have two conditions here. If the conditional independence assumption holds, discriminative and generative methods perform similar. However, if the conditional independence assumption does not hold, discriminative methods outperform generative methods. On the other hand, if the data is finite, that means if we have finite data points and attribute features, naive Bayes is faster and it requires usually big O of log D to converge to its asymptotic error, which is the minimum error, whereas the logistic regression discriminative requires big O of D. So why the independent class conditional densities have an effect on the working of discriminative and generative methods? Because of the parameters estimates are not coupled in the independent features, and each parameter is learned independently, not jointly from the training data. So here is the final verdict about the naive Bayes and logistic regression. Both of the methods learn a linear decision boundary. Naive Bayes makes more restrictive assumptions and has a higher asymptotic error, but it converges faster to its less accurate asymptotic error. So here are some experimental comparison, and it is done on 15 datasets from UCI machine learning repository and 8 continuous features and 7 discrete attributes. So as you can see, naive Bayes is usually converging faster to its asymptotic error. So here is the final recapitulation about the facts that you should know about both of the models. So first, logistic regression is a linear classifier. That means it will learn a decision rule which is a hyperplane to that will assist you to classify examples from positive to negatives or different classes, and the data should be linearly separable. Logistic regression is optimized by maximizing the conditional likelihood. So as you recap, in the linear regressor, you had a closed form solution or the normal equation, but in this term you do not have the closed form solution. Instead you have a concave method. So for the concave method, you use the global optimum with the gradient ascent, which is the opposite of the gradient descent. However, gradient ascent is equal to gradient descent. So on the other hand, Gaussian naive Bayes with the class independent variance is representationally equivalent to the logistic regression. Solution differs because the objective loss function differs for both of the methods. So in summary, uh, the naive Bayes and logistic regression make different assumptions. Naive Bayes makes assumption about the feature independence about given class and assumption about the p of x given y. Logistic regression is a function form of p of y given x and no assumption about p of x given y. About the convergence rate, naive Bayes usually needs less data and logistic regression usually gets to better solutions in the limit. So if you want to read more about the topic, you can go through the chapter 4 of the pattern recognition and machine learning reference book. And apart from that, I would highly suggest you to go through the reading material provided along with this lecture. That concludes today's lecture, and if you have any question, feel free to ask me. Thank you very much.